This is the lecturette for section 12.4, which examines the bonding in solids. And the two kinds of solids we've looked at are ionic solids and metallic solids. And so we're going to start with ionic solids and talk about the control of ionic bonding in solids, why some ionic compounds have stronger ionic bonds, and those some weaker. And then we'll talk about ways we measure bonding in ionic solids, which we classify its strength as something called lattice energy. And we're going to use Born-Haber cycles to do that, which is a special case of Hess's law. And then we're going to look at bonding of metallic solids and other extended solids, and the theory we use for bonding there called band theory. So let's start by looking at just trends in ionic bonding. And what we see is that in general, smaller ions lead to stronger bonding, and higher charges lead to stronger bonding. We're introducing a new measurement here. U, the capital U, stands for lattice energy. And lattice energy is the energy associated with breaking an ionic compound apart to separate its ions. So if you take a mole of sodium chloride and you completely break it apart into ions, you'd make gas phase chloride ions and gas phase sodium ions. The energy to do that is equal to the lattice energy. And so if you look at the lattice energy and melting point, those two track each other as you would expect. And what you see if you look at these three cases here, fluoride is the smallest ion. They all use lithium, which is the same size, but as the anions get bigger, the bonding gets weaker. As the anions get smaller, the bonding gets stronger. If you compare lithium fluoride to sodium fluoride, lithium is smaller than sodium, and you'd expect it to have stronger bonding, and it does. And therefore, also lithium fluoride has a higher melting point. It should have a higher melting point, but in fact it doesn't. Wonder why that is. Okay. Now, the last case is magnesium oxide, which has a much, much stronger lattice energy and a much, much higher melting point. And that's because magnesium oxide is made of magnesium 2 plus ions and O2 minus ions. And all of these other ones are made of one metal and one anion. Anions and metals with +1 and -1 charges each. And so what happens is you would expect this to be about 4 times stronger, because it's the product of the two charges, 2 times 2, versus 1 times 1, than those other ones. And indeed it is about 4 times stronger. So the charges on the ions have the biggest effect, and the sizes of the ions have a more minor but important effect. Next thing we're going to do with this rather cluttered screen is look at determining the lattice energy. And the way we do this is you can't actually measure this reaction. There's no good experimental way of doing that. So what we do is we determine it indirectly by looking at a lot of other things we can measure, and then using all these things we know to figure out what the lattice energy must be by difference. And so what we do is we're using what's called a thermodynamic cycle. And so the idea here is if you start with sodium, so the reaction we're looking for is sodium plus 1 mole of sodium plus a half mole of Cl2 gas goes to make sodium chloride. And so, this is not the lattice energy. What we're looking for is, that should be Cl minus gas and sodium plus gas. That's the lattice energy. So this is what we're looking for. And so what we do is we kind of conceptually build up a sodium chloride crystal. And so what we're going to do is we're going to start with sodium, and which is a solid, and we're going to turn it into gas phase atoms. And that energy is called the energy of sublimation, the enthalpy of sublimation for sodium, which is a measurable quantity. It's 107 kilojoules for 1 mole of sodium. The next thing we're going to do is we're going to take the sodium, and we're going to take an electron out of it, because we have to make ions if we're going to make our salt. And so that's the ionization of sodium, so we know that. So we do that for a mole of that. Next, we have to arrive at our chloride ions. So first thing we need to do is we're starting with Cl2 in our process we're looking at. And so what we're doing is We have to break a half a mole of Cl-Cl bonds to get a mole of Cl atoms. We know the chlorine-chlorine bond energy is 242 kilojoules per mole of Cl2 molecules. So we use half of that to get a mole of Cl atoms. So that's 121 kilojoules. So that's that part right there. Then we need to add an electron to the chlorine to get chlorine minus. That's the electron affinity, and that's actually a favorable process, so that goes back down. So that's our 349. We also know that the enthalpy of formation of NaCl is 411 kilojoules. Now what we can do is we can take our sodium and essentially turn it into sodium plus. We take our chlorine and turn it into Cl minus. The last step is the lattice energy. It's actually minus the lattice energy. And so these steps, here to here and here to here and there to there, should be the same as that step there. So that is the delta H of formation for sodium chloride ought to equal the sum of all those other steps. And so that's what you do. You set the enthalpy of formation of sodium chloride, which is 411, equal to all these other things, and then you solve for the lattice energy. And when you do, you get this step here as being minus 786 kilojoules. So therefore the lattice energy, which is the process to do the opposite, to break the ions apart, is plus 786 kilojoules. So you know everything except that when you do this calculation. Now we turn to metallic bonding. The idea of metallic bonding is based on an extension of molecular orbital theory. And the idea is if you had, say, sodium atoms, or you make a chunk of sodium metal, if you have one sodium atom, it has a valence orbital of 3s. And so if we draw a little molecular orbital diagram, it's got a 3s orbital with one electron in it. So that's a sodium atom. If you have two sodium atoms, you'd actually have two orbitals, and the two electrons would be down there. And they're more stable because they're lower in energy, so that's a bonding orbital. And that would be an antibonding orbital, but it's not filled. Na3 would be here, here, and here. And you'd have 3 electrons in it. Na4 would have here, 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 and here, and you'd have these filled. And the idea is, oh, that's not filled. The idea is if you filled up, if you made a very, very large chunk of sodium, you'd have a whole lot of orbitals. And those whole lot of orbitals would get closer and closer and closer together. And the idea is when you have millions and millions of atoms in a solid, you have millions and millions of orbitals in that solid state, essentially very large molecule, and that's called a band of orbitals. And depending on the particular atom you have and how many electrons that atom has when it's making the solid, this can be at different levels of filled. Not all of those orbitals have to be filled. In the case of sodium, because each orbital starts with 1 electron and can hold 2, sodium happens to be exactly half filled. And as we'll see in a minute, that's not true for all other things. Okay, so the next thing we want to do is we're going to look at trends in metallic bonding. And remember, the idea here is that when we're forming these forming these new orbitals, the ones that are lower in energy are bonding. That is, if electrons are in those orbitals, that is these ones here, the metal is held together. The ones up here are antibonding. And what that means is that if these orbitals have electrons in them, that tends to push the atoms of the metal apart. So let's go ahead and look at a simulation that kind of does an example of this. What we're going to do is we're going to look at the transition metals going across the S and D blocks. And if we start with potassium, what we see is that our bonding band, this is our band of orbitals here. The lower half is bonding, the upper half is antibonding. If we have potassium, it's got electrons in bonding orbitals, but not very many of them. And our melting point is actually relatively low, which means that the potassium is not held together very well. If we go to calcium, we now have more electrons in bonding orbitals, so the bonding should be stronger. And in fact, the temperature, the melting point has gone up a lot. If we go to scandium, the element with the ugliest name, it's actually more bonding. Titanium's more bonding. Vanadium's more bonding. When we get to chromium, we've filled up all our bonding orbitals, and our melting point's now really, really strong, really, really high. So our bonding's really strong. When we go past chromium, we'll start filling up our antibonding orbitals. And when we do that, the melting point will start going down again because we're filling up orbitals, filling electrons into orbitals that actually push the metal atoms apart. And so when we do that, we see that as we get far to the right in the periodic table, we've filled up our antibonding orbitals, and our melting point has then gone down again because we are counteracting our bonding. You can do the same thing down in these other fifth and sixth periods. And when you do this, what you see is that as you go about halfway across the period, you've filled up the bonding orbitals, and tungsten, which is the metal with the highest melting point, has a melting point in the thousands, 3,000 degrees. And when you go past that, it starts going back down again, getting all the way to mercury, which has a melting point below room temperature, below 0 degrees even, and that's a liquid at room temperature. So our general trends is that as you go across the S&P blocks in the periodic table, the strongest bonding is when you've got the band half filled, and those are the elements around group 6b, around the chromium, molybdenum, tungsten group. And as you go to either side of that, the bonding gets weaker. An extension of this band theory is used for describing and explaining semiconductors. What happens is, if you have, these are 3 different kinds of bands for the 3 different cases down here, and all of these are what are called conductors. And the idea is that they conduct electricity. And the reason is that these, where it's shaded, are filled, and where it's unshaded, it's empty. But there are orbitals there. And the idea is if an electron is going to move through a solid, it has to get from one place, one atom, to another atom, and which means it goes from one orbital to another orbital. And here, an electron only has to jump from here, stop that, from here up to here. It has to jump a very little amount to get from a filled orbital to an empty orbital. So in any of these cases, doesn't matter which, the electron only has to jump a tiny bit. So anything with a partially filled band will give a conductor. If, on the other hand, you have a band structure where you have a completely filled band, a totally filled band, and then an empty band, but there's a big energy gap there, that energy gap means the electron would have to jump all the way up to there in order to get to a new orbital, in order to move, to conduct, and so this is an insulator. Okay, a semiconductor is something in between. It's where the gap is really moderate, not very big, but not really, really small. So in the insulators, it's really big. In the conductors, it's tiny. But in a semiconductor, the band is really small, but it's appreciable. So this is called an intrinsic semiconductor. And that's because you have a filled band with an empty band not much above it. There aren't very many semiconductors like that. Semiconductors that are important are actually synthetic or doped semiconductors. And the way they work is they work with silicon. So silicon actually has a filled, what's called valence band, and then an empty, what's called conduction band. And actually silicon in and of itself is an insulator. We turn it into a semiconductor by adding an impurity, and those impurities can, for example, add a set of orbitals slightly above the orbitals for the silicon. And so these are the impurities. And these particular impurities right here would be something like boron or aluminum or gallium would add these particular impurities. And they essentially put orbitals that have vacancies in them slightly above, and you've made a new little gap there. And by doping the silicon, you can essentially tune your band gap, how big that gap is and how much the electron how fast the electron can conduct, by changing what these impurities are and how much are there. And so that gives us control over our semiconductors, so we can make semiconductors with different properties. And all of the computer chips that you use and all of the calculators and cell phones, they all use silicon chips that are doped this way, or with actually a different kind of doping that actually puts orbitals down or up there. That's how it works.